Hi students, this is VLSI Design. Today's our topic is building blocks presented by Subhash Devi. After completion of this topic, students will be able to define shift registers and types, define FIFO and LIFO. Decoders. Here we are using the 2 power n input decoders. Here using this one n into 2 power n decoder, that means n input is given and 2 power n output is produced in the output session. 2 power n means if you suppose we are using 2 bit means 2 power 2, 2 2s are 4 output session is produced. So decoders only used here. One needed for each row of memory. Built and from NAND or NOR gates. We are using to build NAND or NOR gate. Here we are using static CMOS and then pseudo NMOS is shown here. Static CMOS means same input is given to the both session, and then pseudo NMOS means it's a inverter session is shown in the here. How to implementation is followed in the decoder session. After that, decoders layout is shown here. Decoders must be bits matched to SRAM cell drag bars. Very skinny gates is followed. That's why we are using this layout diagram here. Large decoders means here we are using the 4 bits or greater than 4 bits is used to implement. That means how to implementation is followed in the diagram. NAND gates become slow, break large gate into multiple smaller gates. That's why we are using. If here shown the 4 bit is shown, so for 2 power 4 combination it will produce the output session. 2 power 4 means 2 2s are 4, 4 2s are 8, 8 2s are 16 bit 18 16 combination it will produce in the output session to the power 4. That's why 16 combinations it will produce in the output session. Pre-decoding. Many of these gates are redundant. Factor out common gates into the pre-decoder saves the area same path effort. Here we are using the pre-decoding. If after decoding we are having some more number of gates will be followed, that's why we are using the pre-decoders here in the use this session. That's why we simplify it. 1 to 4 hot pre-decoders lines will combine together and it will reduce the gate. Multiple parts will be enabled. Here multiple ports are used. We have considered single ported SRAM, one read or one write on each cycle. If multiple ported means multiple ported SRAM are needed for register files. For example, multi-cycle means must read two sources or write a result on some cycles. Pipeline means must read two sources and write a third result each cycle, and superscalar means must read and write many sources and results each cycle. That's why we are using the multiple ports. Dual ported SRAM shown here. Symbol dual ported SRAM. Two independent single-ended reads or one differential write is shown here, and do two reads and one write of the multiplexing. After that, multi-ported SRAM is shown here. Adding more access transistors hurts read stability. Multi-ported SRAM isolated reads from state node. Single-ended design minimize number of bit lines. Serial access memory. Serial access memory do not use an address. It will use the shift registers, tapped delay line, serial in, serial out, parallel in, serial out, and queues. Like that, serial access memories we are having these sometimes. Then shift registers. Shift register for only store and delay data. Simple design is enabled for cascade and registers. This is shown in the here. Watch your hold times. Then next one, tensor shift registers. Flip-flops are not very area efficient. For large shift registers, keep data in the SRAM instead. Move read and write pointers to RAM rather than data. Initialize read address to first entry, write to last. Increment address on each cycle. Here we are having the diagram of these 10 shift registers. Tapped delay line. A tapped delay line is a shift register with a programmable number of stages. Set number of stages with delay controls to max. For example, 0 to 63 stages of delays we are shown in the here 32 delays is shown. Then serial in parallel out. 1 bit shift register read in serial data after the n steps present the parallel output. Here we are giving the input in this line. After that we get single bit from this parallel output. That's why we are using a number of steps will be increased. Serial, for example, serial in parallel out is registers. After that, parallel in serial out. Load all n bits in parallel when shift equal to 0. When then shift 1 bit out per cycle. This is the maximum we are using the shift registers. Left or right shift we are followed in the serial in parallel out and parallel in serial out registers. After that, queues. Queues allows data to be read and written at different dates. Read and write each use their own clock data. Queues indicates whether it is full or empty. Built with SRAM and read-write counters pointers. This is the queues symbol diagram. Then FIFO and LIFO queues. First in first out is shown first one. Initialize read and write pointers to first element. Queues is empty. One write increment write pointer in a write almost catches read. Queue is full. On read increment read pointer lost in first out LIFO, also called a stack. First one is queue, second one is FIFO is a queue, LIFO is a stack. Use a single stack pointer for read and write operation. After completion of this session, we can able to give the quiz question, give the difference between PROM and EEPROM.